Alright, so in my example, I have a small electron. An electron is one small part of an entire atom. So atoms have many electrons, and electrons have negative charge. So they are the building blocks of atoms. They are charged with a negative charge. And the units of charge is coulomb. From physics, it's coulomb. And from physics, there is a law that says that if a charged particle travels with some kind of velocity through a magnetic field, now these crosses here, they're magnetic fields, and they're denoted with B. So the reason why you have crosses here is, do you remember this notation that this comes out of the plane and this goes into the plane? So a magnetic field is a vector, and in this example the vector goes right into the plane, into my sheet of paper. So negative z-axis. So here we define z to be positive, so out of the paper like this. And the magnetic field is in the opposite direction. It goes into the plane, so in the negative k direction. And the velocity travels in the positive x direction. And then you can see from this formula that there will be a force applied to that electron if it has some kind of velocity and if it travels through a magnetic field. So both of them need to exist. A magnetic field needs to exist in order for the force to be something else but zero, and also the electron needs to travel at some kind of velocity in order to have force. So if the particle is at rest in the magnetic field, then there is no force. But now we assume that it has a velocity, so it travels, and this is defined v cross b. Now, what would be the direction of the force just by thinking about the right-hand rule? Well, so if my electron moves through the magnetic field in this way, so this is the velocity, and then if the magnetic field, if its vector points down, then my thumb goes up. So I should have a force in this way, right? So the particle should go in this direction at some kind of velocity, and then the magnetic field will point down, and then the force goes here. So the force should be in this direction, right? However, don't forget that the electron has a negative charge. So charge is a scalar quantity. So even though the velocity is like this and the cross product says that, okay, if I just cross it with the magnetic field, then the force points that way, and that would be true for a proton that has a positive charge. But since the electron has a negative charge, it will reverse the whole thing. So the cross product gives me this direction, but since I have a negative scalar, then the force will be in the opposite direction. So the force will not be up, it will be down. Because even though the cross product tells me that I should go that way, but since I have a negative charge, I will go that way. I will go down. So what will happen then? So my electron goes through the magnetic field, and instead of having a force up, because of the negative charge, we have a force down. From the moment it enters the magnetic field, right, from the moment it's here, it will have some kind of force there. Now, the particle still has velocity into the x direction. It will continue moving forward, but then there is also this force pulling it down. So it will move something like this. But then what will happen with the force? Because remember, it will go there, but now it has also gone in this direction, right? So now not only you have the Vx component, you also have the negative Vy component. The force has pulled the electron down, so it still goes forward, but it has also moved down. So now the velocity vector, the magnitude of those two components, will give you a vector in this direction. So now you have the new velocity in this direction, but the magnetic field is still down. So the cross product would give you this direction, but since you have a negative charge, then your force in fact will be perpendicular to velocity and the magnetic field, and it will be in this direction. I'm just gonna draw it here again. So the velocity now is here. That force will cause the particle to go in this way, right? In this direction. So at some point, the velocity is in this direction and the magnetic field is down, and the force will be in this direction. So that would be the force vector. And then etc., etc. So what will happen? Well, the electron, for as long as it remains in the magnetic field, it will go in circle, right? It will just go in circle. And that's how scientists, that's how they control those small particles that have charge. They control them with magnetic fields. They give them some kind of velocity, then they establish some kind of magnetic field, and that will cause the electrons to move in circles. And then by varying the magnetic field and the velocity, you can vary the force. And if you vary the force, then you can control how those particles move. Okay, so this is a real-life application where you can apply the cross product. And of course, once you know the real values, the real charge, the real velocity, the real magnetic field at any instance of time, because this is at time equals 0, this is at time equals, well, it would be 0.0000 something. So once you have those values, then for each time you can just use the formula that I gave you in the previous video to calculate the real force, and then from that you can also know the trajectory. The scientists can know how the electrons will move. Okay, and that concludes the part on vector operations. Now you know how to add vectors, how to subtract them, you know what a dot product is, how to apply it, you know what a cross product is, and how to apply it. And then in the next lecture, you will see how all the functions that we have covered so far can be applied to control the levels of water in the tanks, and how you can manipulate the levels of water in the tanks by manipulating the functions. So you will see the use of what we have learned so far, and it will be very interesting. Essentially, you can use math to simulate a real-life system on your computer when you, for example, write a program for your controller that controls, in this example, the levels of water in the water storage building. It's going to be very useful and interesting. So see you then. Welcome back. In this lecture, you will see how all the functions that we have covered so far can be applied to control the levels of water in the tanks, and how you can manipulate the levels of water in the tanks by manipulating the functions. So you will see the use of what we have learned so far, and it will be very interesting. Essentially, you can use math to simulate a real-life system on your computer when you, for example, write a program for your controller that controls, in this example, the levels of water in the water storage building. So let's get started. I have this water storage building, and now I have 3 tanks, and I want to control the volume of water in each tank as a function of time. So I want to give the computer time, and then the computer will control the levels of water in each tank as the time goes on. And how would I denote it mathematically? Well, I would denote it as a vector. So I could write something like this. Volume total, arrow. This is a vector. And in fact, I would say that it's a function of time. And then I would have the first element, tank 1, as a function of time, tank 2 as a function of time, and tank 3 as a function of time. Now remember what we said earlier, that vectors themselves are not functions. However, each vector element is a function of time. And therefore, if each vector element depends on time, then the entire vector depends on time. Makes sense, right? If you can control each vector element as a function of time, if you can control the volume of water in each tank, and each vector element is a function of time, which means that the time is the input and each vector element is the output, then the entire vector is also as a function of time. So I'm gonna draw a little schematic here. So here you can see how you can control each vector element and therefore the entire vector. So you have this independent variable here, right? This input, time, t. And then you take this t and you put it in the first function here, and you get the first vector element, or the volume of water in the first tank. And then the same t goes into the function 2, and then you have the volume of water in the second tank, v2. And the same thing, the t goes into function 3, the time goes into function 3, and then you get v3. You can control each vector element as a function of time, and then what you do, you vectorize them. And vectorizing means that you just take these outputs, right? v1, v2, and v3 are the outputs, and you structure them as a vector, like this, v1, v2, and v3. So you vectorize them, and you get the total volume of water as a vector per each tank. So you will have different functions here, so you can control each volume in the tank differently as you please, and essentially they will be the instructions for the computer to, let's say, give orders to the pumps that would control the level of water inside the tanks. Now, this is a visual way to represent your system, just to have a visual understanding of your system. A mathematical way to represent it would be like this. The vector of the total volume of water as a function of time would be f1t, f2t, and f3t. Or you can also write it like this. I'm just going to write it here. f1t unit vector I plus f2t unit vector j plus f3t unit vector k. And this, in calculus, it's also called parametric equations. So let's see how we can control the volume of water in the tanks. Or in other words, how we can control these vector elements as a function of time. Those vector elements, they depend on the variable time, how we can control them. And we're going to assume that the pumps that we have here that control the water, that make the water flow in and that suck the water out of the pumps, we assume that those pumps can cope with whatever orders we give them. So even if we put some kind of bizarre function, then we assume that the pumps can cope with that. Even though in real life, of course, you have to take into account that, okay, what I want to happen, can the pumps really do it? But here we're gonna assume that they can do whatever we tell them to do. Alright, Let's define our initial conditions. So the initial volumes of water inside the tanks are written here. So V1I, I stands for initial. So V1I is 50 cubic meters. So at the beginning, when time equals 0 seconds, then in the first tank you have 50 cubic meters of water. In the second tank you have 40 cubic meters of water, and in the third tank 30 cubic meters of water. Now, task 1. Task 1 is program the controller to order the pumps to increase the water levels in each tank by 2 cubic meters a second. So even though we have different levels of water in each tank at time equals 0 seconds, we want to order the pumps to add every second 2 cubic meters of water into each tank. Alright? And the total volume of each tank is 100 cubic meters. So I want my program to stop when the volume reaches 95% of the tank. So you start adding the water when it reaches 95% of the tank, then I want it to stop. So obviously you can already think about it that if I add 2 cubic meters of water per second to each tank, then the change of volume in each tank will be the same. And since this one has more water inside at the beginning, the first tank, it will reach 95% of its volume first. And then the second tank will reach it, then the third tank will reach it. So the first tank needs to stop first, then the second tank needs to stop, and then the third tank needs to stop. So how would we control it with functions? Well, we have something called piecewise defined functions that we had covered earlier. So our limit, our maximum volume that we can have, would be 100 times 0.95 would be 95 cubic meters. So we cannot have more water than that inside each tank. Let's just start with the first tank. Our initial condition is 50 plus, and the rate of change will be 2 cubic meters per second. So it's 2 times t, right? So every second 2 cubic meters of water will be added to the tank. Now, in order to know when to stop the pumps, we have to know at what time it will reach 95 cubic meters. So what we can do, we can simply calculate the time. We can say that 50 plus 2t equals 95. So it will be 2t equals 95 minus 50. And of course, to find the time, we have to divide it by 2. So that would be 45 divided by 2. So the time in this case would be 22.5 seconds. So I can very simply write controller, follow this instruction, follow this function from time equals 0, 0 included, time, and up until 22.5 seconds. And then time after 22.5 seconds, your water volume should be 95 cubic meters. So it's a piecewise defined function here, you see? So first of all, you increase up until 22.5 seconds. The computer increases it, the program increases it. So this will give you volume, cubic meters. So it's cubic meters per second times time, which is seconds. So cubic meters per second, which is 2, times time, which will give you seconds. then you cancel them out, and you will get volume here plus this volume here, and then at t equals 22.5 seconds you will get 95, and after that the program shuts down. All right, in the program you can write it like with an if statement. Okay, if time is less than 22.5, then use this function. If it's bigger, then use this function. Okay, let's take the second tank now. So in the second tank, our equation would be 40 plus 2t, and again 95. So in order to find time when we have to shut down the second tank, in order to find that, we need to just calculate the time, which is 95 minus 40. You would divide it by 2. So time equals 55 divided by 2. And that would be 27.5 seconds. Okay? So our second piecewise equation for the second tank would be 40 plus 2t when 0 is less than t and t is less than 27.5 seconds. So this is seconds and this is volume here. And then after that you will have 95 cubic meters after t is greater than 27.5 seconds. So let me also squeeze the third tank onto this page. So the equation for the third tank would be 30 plus 2t equals 95. We initially have 30 cubic meters of water, then we start adding 2 cubic meters of water a second, and we have to find the time, which would be 2t equals 95 minus 30 divided by 2, then we cancel it out here, and we will get 65 divided by 2, which is 32.5 seconds. And now we're gonna just write it down like this. Tank 3 as a function of time, and by the way, the tank 2 was also as a function of time, equals 30 plus 2t when the time goes from 0 up until 32.5 seconds, and then stop or have 95 cubic meters of water in the third tank when the time is after 32.5 seconds. And again, it's a piecewise defined function. So you see, now we are taking all the separate functions that we have been learning so far and we're combining them to describe the real system. Okay, see you in the next video to solve the task 2, the second task. See you soon.